ad recommender stops scoring one item at a time and instead starts generating a whole ranked list like a tiny language model. That is the big move in this paper. But advertising is picky. You need business-aware item tokens, list-wise value optimization, and really fast inference. So the authors build GR4AD with UA-SID for ad tokenization, RSPO for ranking-aware reinforcement learning, and a serving system that adapts beam width to traffic. The fun part is lazy AR. It keeps the hard early prediction strong, then gets lazier later to save compute. The result is a deployed system that reports up to 4.2% more revenue while staying under 100 milliseconds. Tiny decoding drama. Very real ad money.
The industry is currently undergoing a major shift, moving away from traditional deep learning recommendation models toward generative approaches. But here is the catch. You can't just take standard large language model (LLM) techniques and drop them into an advertising system. It doesn't work that way. Advertising systems face three massive hurdles. First, how do we represent ads? They aren't just simple text. They are complex, multimodal entities with business signals that standard tokenization completely misses. Second, the learning paradigm is tricky. Advertising is all about optimizing ranked lists for business value, while most standard models are just focused on individual items. Finally, there is the real-time serving challenge. We need to generate multiple high-quality candidates under extremely tight latency constraints, which is a completely different world from the relaxed timing of a typical chatbot. To bridge these gaps, this work introduces a co-designed system tackling three pillars: specialized advertisements, semantic IDs for better representation, value-aware online learning to align with business goals, and an optimized decoder architecture for high-throughput, real-time performance. To understand how we got here, let's look at the evolution of the field. We are moving away from traditional item IDs towards semantic identifiers that actually capture the content of the ads. The core idea is to use LLMs to turn text and video into embeddings, which are then compressed into structured codes. This is a huge win for the cold start problem, where new items lack interaction data. We also see a shift in how we align models with business goals like revenue. While early methods relied on complex reward models, the field is moving toward DPO to keep things stable. Building on this, the authors introduce a unified advertisement semantic ID. They fine-tune a model using specific instructions to understand different ad types and incorporate collaborative signals, like how often items appear together, to make these representations much more relevant to real-world advertising needs. Now let's dive into the technical heart of the system. How do we represent these ads? The authors use a contrastive learning approach, specifically the info-NCE loss, to ensure that related ad components, like video, product, and advertiser data, are grouped together in the embedding space. To make these IDs even more robust, they use a multi-resolution clustering method. This breaks an ad into a sequence of tokens across different levels, capturing both broad categories and specific business details. They even use a hash-based mapping for non-semantic data to prevent collisions, where different ads accidentally get the same ID. Moving on to the decoder, they introduce the lazy AR decoder. Standard models generate tokens one by one in a strict chain, but this decoder is different. It processes a context of features and then generates the target sequence. By moving away from that rigid step-by-step prediction, the system handles the high-speed, high-volume demands of real-time advertising without sacrificing quality. This brings us to lazy AR, which is a really clever way to speed up the generation process. The authors noticed that in standard autoregressive models, the system wastes time recalculating the same early layers for every single beam candidate. To fix this, they split the decoder into two parts. The first part, the trunk, computes the initial layers without needing to know the previous token. Because this part doesn't depend on the previous step, it can be computed once and shared across all beams. A massive efficiency win. Then, they use a fusion operator to inject the previous token's information into the model at a middle layer, allowing the remaining layers to finish the job autoregressively. By tuning how many layers are in the trunk, they balance speed and accuracy perfectly. It essentially turns a computational bottleneck into a shared, reusable resource. Now let's talk about the secret sauce for prioritizing business value. First, there is ECPM-aware training. Instead of just predicting the next item, the model predicts a discretized value token representing the expected revenue. This forces the model to care about money, not just relevance. They also use sample weighting, giving more importance to training data from high-value users or deep interactions like purchases. Then, they tackle the reinforcement learning side with RSPO, or Ranking-Guided Softmax Preference Optimization. Instead of just comparing two items, RSPO looks at the entire ranked list. It calculates how much the ranking metric, specifically NDCG, would improve if the model swapped the positions of two items. It then updates the model to favor swaps that boost overall list quality. Finally, they include a reliability gate, a safety mechanism that checks if the model's current predictions are drifting too far from a stable reference. If the drift is too high, it ignores the reference to keep training stable. How does this work in the real world? The system uses a closed-loop architecture that is constantly learning. They use a real-time index that maps ads to semantic IDs. Unlike older systems that needed slow, frequent index rebuilds, this approach is stable and allows new ads to be indexed in seconds. They also manage the training balance using a rank discrepancy metric. If the model's current ranking is far off from the ideal reward-based ranking, the system prioritizes supervised learning to get back on track. If it's already well aligned, it shifts focus to reinforcement learning to squeeze out more business value. Finally, they tackle efficiency with dynamic beam serving. Instead of using a fixed beam width, which is often wasteful, they progressively increase the beam width during the generation process and adapt it based on real-time traffic. This keeps the system fast during peak hours while still delivering high-quality results. The results really tell the story here. Look at the table provided. It acts as a roadmap for the paper's contributions, showing exactly how much each piece, the semantic IDs, the value-aware learning, and the efficient decoder adds to the bottom line. It's fascinating to see that while some learning optimizations actually cost a bit of throughput, the serving optimizations more than make up for it, leading to a huge jump in overall efficiency. The authors explain that their ranking-guided optimization captures user preferences much better than standard methods. They also highlight that their efficient decoder design, which shares layers across different beam candidates, is the key to handling the massive traffic at Kuaishou without breaking a sweat. It's a great example of how balancing model quality with engineering constraints leads to a win-win for the platform, the advertisers, and the users. To wrap things up, the authors prove that scaling really works. Both increasing the model size and widening the beam search during inference lead to clear, measurable gains in ad revenue. It's a classic more is better scenario, but they provide the data to show exactly how much revenue you get for your computational buck. They also take a deep dive into the quality of their semantic IDs. By comparing different embedding and quantization methods, they demonstrate that their specific approach, using a vision language model with instruction tuning, creates much more accurate and efficient identifiers than previous methods. Check out the table on this page. It shows that their final design minimizes collisions, where different ads get the same ID, and maximizes how well the system uses its available codebook space. In conclusion, this co-designed system, covering everything from how ads are represented to how the model is served, is exactly what makes generative recommendation viable for the massive, real-time demands of a platform like Kuaishou. Thanks for joining us today. Happy exploring together!